Hello everybody again. This video is going to cover the charging and discharging of inductors in a DC environment. And we're just going to jump right into it and start looking at it. Excuse me. So inductors, charging and discharging in DC. So we're talking about something of this nature. Okay. Here's an inductor, and I know I'm drawing it so terribly. And this second part would sort of be, so I'm going to call this our charge, and I'll call this our discharge. Okay, we saw in the PBL that you can actually use a function generator over here, and you kind of don't include this part. It's just one circuit, and the function generator using a square wave sort of mimics the on DC, and then when it's down, it's like the off DC, and it's in discharge mode. But whatever, so this is sort of a generic circuit that allows us to charge and discharge in DC. So I have the battery here, charges my inductor, and then the switch switches over, and then we go into a discharge mode. All right. And I'm not going to go into all the math and everything, because it takes some calculus and whatnot, and we don't care. We don't care. We just want to use the equations. First thing to talk about is the time constant, tau. Okay, so we use tau in both if we're charging or discharging a capacitor or an inductor, because the same thing. It's an equation. It's a circuit. It's a concept. The time constant represents a concept. It tells you how much time it takes to charge or discharge the inductor, right? And again, using calculus, it can be shown that for an inductor, this is the relationship. L over R is tau. And remember, to get to steady state, it's still 5 times tau, right? So great, fantastic. What do the equations look like? So if you remember, I mentioned the previous one that it's really the current that's the important thing in inductors. It was voltage and capacitors. So the current is the key quantity with inductors. So charging looks like this. Oops, sorry, it's not technically, technically it's not a capital. I got to be careful here. Technically it's a small I with a little L as a function of time, and it's I max, whatever I max is, 1 minus e to the minus t over tau. Hey, look at that. Doesn't that look like just like the other equation for capacitors, for charging a capacitor? The only difference is we're looking at VC and a V max instead. This part is the same. So this is your like natural growth curve. And so charging always looks like that, regardless of if you're charging a capacitor, charging voltage, or charging an inductor, charging current. And so the graph, again, I don't think I have to redraw it, but I'll put it over here, right? It's going to look like this, just like the voltage one. Sorry, that should be again. IL of t, this is time, right? This is your I max. And remember around here where t equals tau, it's approximately 63% of I max, right? So all that is the same. That's the beauty of charging and discharging. It doesn't matter which one we're talking about. All you have to do is figure out, is it an inductor or capacitor? If it's a capacitor, we do voltage. If it's an inductor, we do current, right? When we're charging, okay, the V then is in the decay mode. Always. Okay, so just like the current was in capacitance, doesn't matter if we're charging or discharging, it always uses the decay curve. And there we go. Decay curve. Okay. So, that's what it is. You're going to go into more detail in AC about this, but that's the starting point. And I'm trying to just keep this short because, again, it's similar to the capacitors, except we're talking about current here for the inductor rather than voltage for the capacitor. And we're talking about voltage here rather than current in the capacitor. All right, so when we're in discharge, then our current looks like this. IL of t equals I max e to the minus t over tau. And voltage is still V max e to the minus t over tau. So if we have to graph these things and see them fully, this is what your current would look like in an inductor. IL of t, I max, 5 tau. So we charge up to 5 tau, and we approximately get to the I max. And then we go into discharge mode, and it goes down until we get to almost zero at 5. Well, this is now 10 tau, technically speaking. Okay, time, on one graph. But yeah, from here to there is 5 tau, of course. At tau, that's a terrible tau, but I said tau, so you guys heard me say tau. Okay, this is that 63% of I max. And then at the tau for this one, which is technically 6 tau along my graph, okay, that's 37% of I max. And again, that comes directly from these equations here. You can plug in the numbers, you can plot it, use Excel, prove it to yourself. Okay, don't just take my word for it. Prove it to yourself that it is this. But that's in general what the graph looks like for the current, right? The voltage will look something like this. And again, I'm going to do the split thing because it does the same thing as the current does in capacitors. So we start at a Vmax. We discharge until the 5 tau. Okay, and I didn't draw it well, right? And then it does this because it goes in the opposite direction, the voltage, right? Because now it's acting like a source rather than a receiving stuff, okay? But again, this value here, and of course my lines are terrible, is a Vmax, but negative. Okay, this is 5 tau, this is 10 tau, right? At tau, we were at 37% of Vmax. I don't know why I keep wanting to write a W instead of a V. 37% Vmax. And at this tau, which is 6 tau along the full thing, but that's just a single tau for this. And of course, I'm not to scale, okay? So don't get freaked out over here, okay? But again, it's 37% of this minus Vmax. So really, that's all I want to say. These two equations, charging, discharging on an inductor or in an inductor, we could see that it's the current that's the important one. The current must remain constant or continuous. Continuous is the right word in an inductor. Again, if you stop and think about it, it's a wire. You can't just abruptly stop uh, current. Okay, we can't have an accident on the highway and everything stops instantaneously. Things happen slowly, right? So the current in inductors gotta, if you're charging, it's gotta slowly go up. And then when we go into discharge, it slowly goes down, right? The voltage though is the one that can jump, right? And this is where that spark happens that I mentioned in the previous video. If you're using like a power drill and you're kind of looking inside, and inside is an inductor essentially. Not essentially, it is an inductor, it's a coil. And so, discharge, and then snap and bounces, across. And so this is where you can kind of sometimes see that spark in a drill when you get that switch between. And it's because of this idea that the voltage can jump and can change really quickly, right? On paper, this is how we draw it. There's no chance of any shock or any sparks or anything. And that's about it. That's all you really need to know about inductors in DC circuits at this point. You'll go into it a little more detail next semester in your AC circuits, but all I can say is good luck, and we'll see you in the final.